All right. Good morning, everyone. Thanks for coming to the talk. I apologize for not being Sangeeta. Oh, start my video. Okay, just got a notification. Okay. All right. So yeah, I will be presenting Sangeeta's slides, and this is this is work that I'm also involved in, particularly with the narrowband searches for Lyman-alpha emitters through the Logger and CIDR surveys, and also work leading up to the launch of the Roman Space Telescope that's slated to happen next year. So this is our group's efforts to use Lyman-alpha emitting galaxies to probe the epoch of reionization. And on this title slide, I'm showing the the cartoon picture of the history of the universe with the Big Bang on the far left and the present day universe at the far right. And in between is depicted this major phase transition that we're interested in of reionization. And this is going from a neutral to an ionized regime, which is instigated by the formation of the first stars and galaxies, which ionize bubbles around them, eventually ionizing the universe. And what we'd like to do is probe this epoch with Lyman-alpha emitting galaxies. And so the idea here is that as we survey populations of Lyman-alpha emitters at higher and higher redshifts, we expect their number densities to significantly decline. We expect the strength of Lyman-alpha emission, or the equivalent width, to decline. And we also expect them to be preferentially located within ionized bubbles, and this should be reflected in an increased signature of their clustering. They should be more clustered as we go into this epoch of reionization. Can people see where my cursor is at?
Yes, yes.
Okay, great. Okay, so that's sort of like the premise of how we'd like to use Lyman-alpha emitting galaxies. And so why is it that we would expect these galaxies to disappear as we go into this epoch? And this is because Lyman-alpha emission is resonantly scattered by any neutral hydrogen that it encounters, whether that's in the ISM or IgM. And so here is showing this energy diagram where Lyman-alpha emission is produced when the electron transitions from the first excited state down to the ground state. And so this means that when Lyman-alpha is traveling through the medium, if it encounters any neutral hydrogen, it can be readily absorbed, resonantly absorbed, and scattered in a random direction. And so here's a few cartoon pictures to kind of illustrate the different idealized scenarios. So if we were to picture an ionizing source, and so here we're imagining a young starbursting galaxy producing Lyman-alpha emitting photons along with a UV continuum photons. And in the case where you have a completely ionized medium, these photons can travel directly to the observer. However, if we have a neutral medium, we expect the Lyman-alpha photons to have a significantly larger path length because they are, traveling along this random path. They're being resonantly scattered by the neutral hydrogen that they encounter, as opposed to the UV continuum photons, which can more directly travel to us. So a kind of a middle scenario would be where you have a young starbursting galaxy that exists within an ionized region. And in this case, some of the Lyman-alpha photons, particularly the Lyman-alpha photons that happen to exist in the red wing of the line profile, could potentially be travel directly to us. However, the blue wing, we would expect to again experience this random walk and be harder to detect. So, this is the idea of, as we go into this reionization epoch, Lyman-alpha emissions should be harder to detect, their number densities should decline rapidly, and their clustering should increase. And so these Lyman-alpha tests are probes of the local IgM. It is scalable. We have the technology to do these Lyman-alpha tests right now. There are no significant foregrounds, and we can determine the topology of reionization with a large enough sample. So these are samples that will enable us to do clustering analysis. So these types of tests are of course more powerful when we combine them with other tests of reionization, including 21 centimeter studies. And Lyman-alpha is particularly good at constraining the central portion of reionization. So this is a cartoon picture that Sangeeta has shown quite a bit, and I'm not going to do it justice. I'm sorry, but I can explain here. So in this cartoon picture, you have different folks have they have their own favorite reionization probes, and you can get different pictures of, for example, the tail end of reionization or the middle portions of reionization. And so, this all these different pictures of reionization are better when they are combined, giving us a full picture of the elephant here, which is representing reionization. So one of our group's efforts to constrain reionization with a Lyman-alpha narrowband test is this LAGER project, which stands for Lyman-alpha Galaxies in the Epoch of Reionization. So this is a narrowband survey looking for Lyman-alpha emission at a redshift of 6.9. It's using it's employing the 4-meter Blanco telescope in Chile. This has the dark energy camera, which has an extremely large field of view of 3 square degrees. So this gives us enough volume to really place meaningful constraints on what's happening with the neutral hydrogen fraction in the intergalactic medium. And so this is a specially designed narrowband filter designed to fall in between bright skylines, allowing us to detect Lyman-alpha emission within a narrow redshift slice at a redshift of 6.9. So with these 3 square degree fields, we are going to do a total of 8 of these when LAGER is complete. We have published 4 out of the 8, finding on the order of 300 Lyman-alpha emitting candidates. We have spectroscopically followed up on the order of around 50 of these objects. Our latest spectroscopic results are presented in Santosh Harris's paper in 2022. So here we are finding a spectroscopic success rate, confirmation rate of 80%, which is quite high, demonstrating that we are able to efficiently identify high confidence Lyman-alpha emitters. And we also co-added all of these spectra together, looking for high excitation UV lines that would indicate AGN, but we do not find this with our current spectroscopic stack. Okay, so going into more familiar territory for me. So, my work has focused on doing these number density tests. So we're looking for, do we find evidence of a rapid decline in their number densities? And so this has shown the number density of the Lyman-alpha emitting galaxies as a function of their line luminosity. And this is the halfway point for the LAGER survey, showing 4 fields: wide 12, gamma 15, Cosmos, and Chandra Deep Field South. And so the main takeaway here is that, all of the the fainter Lyman-alpha emitting galaxies for the 4 different fields, we're finding very consistent number densities. But when we look at the bright end, we find that some of the fields have this bright end bump, and in particular, Cosmos shows a significant bright end bump. And we find that these very bright Lyman-alpha emitters are preferentially located in overdensities. And I have a slide later on that goes into more detail showing this overdensity that we're finding within Cosmos. And on the right, I'm just showing that when we fit these four different fields with Schechter functions, we find that their best fit Schechter functions are in agreement with each other within 1 sigma. So when we take all four of these fields and we combine them into our halfway point best number density constraints for logger, this is the result, this red curve. And so we've compared our result to archival studies, and we find that, there is a decline as we go from redshift of 6 to 7. So from redshifts where we'd expect the IgM to be fully ionized to logger's redshift at approximately 7. However, this decline that we see is relatively modest. So it is this decline that we see is roughly consistent with what we see in the parent population of UV selected galaxies over the same redshift regime. So this does not leave a lot of room for the IgM to play a major role in preventing us from observing Lyman-alpha emitters. And so when we quantify this, this is shown in this figure here. So our constraints on the neutral hydrogen fraction are shown by this red limit. So we are finding a neutral hydrogen fraction that is 33% or less. So this is consistent with a fully ionized universe at a redshift of 6.9. And this is a result that has been found with some of the Subaru studies also at a redshift of 7. So this figure is attempting to compare our constraints of the neutral hydrogen fraction with other available constraints within the literature. So we're looking at not only our logger results, but other number density, Lyman-alpha number density constraints, Lyman-alpha clustering constraints, the Lyman-alpha equivalent width, or how the strength of Lyman-alpha emission is declining, which can also be used to constrain the neutral hydrogen fraction, along with quasar and gamma ray burst constraints. And the main takeaway from this figure is that despite all of these many different observational constraints, they are still roughly consistent with many different reionization scenarios. And they offer many different, a diverse set of different types of galaxies that are driving reionization, and the length, and also the onset of reionization. So if, for example, this black line is the reionization model that is presented by Finkelstein et al. And in this model, you have low mass galaxies that are primarily driving reionization. And this results in an early onset of reionization and a very gradual transition from fully neutral to fully ionized. And this can be compared to a model like Naidu et al., where you have a reionization that is driven by more massive galaxies, and it results in a relatively late and rapid transition. And so, we want to conduct Lyman-alpha probes and be able to constrain the timing, which will help us to identify which models are favored and help us to constrain what types of galaxies are actually driving reionization. So with the completion of logger, we're going to double our volume that we're able to use to constrain the neutral hydrogen fraction. We're also interested in constraining using Lyman-alpha test at higher redshifts, which I'll go into in the next few slides. But before I move on from logger, let me just highlight the protocluster that we found within the Cosmos field. So here, this is showing the extent of the Cosmos field. All the blue dots here are different Lyman-alpha emitters that have been identified. And you can see that there is this overdensity located within this dashed rectangle. And so here, within this overdensity, is where we're finding preferentially these very bright Lyman-alpha emitters. And this is sort of like a zoom in of the same region. And so here, all of the objects that are filled in, we have confirmed them spectroscopically, and we have relatively recent James Webb follow-up, which are giving us the rest frame optical emission line properties of 9 of these objects. And we expect to post this to our results based on this in the next coming months onto the archive. Okay, so this is and I should state that this is the most massive protocluster identified in the epoch of reionization, and we have spectroscopic confirmations for the vast majority of all of these objects at this point. So another thing that we expect to happen as we move into the epoch of reionization is not only the number density declining, but we expect the equivalent width to decline, the strength of the Lyman-alpha emission to decline. And this is work that's in prep by Sangeeta showing that we actually don't see much decline in the equivalent width from a redshift of 7 to 4.5. And this is consistent with the number density not rapidly declining. So this is work that is in prep for also comparing logger to lower redshift samples. So we are interested in conducting these Lyman-alpha tests at higher redshifts. This is an example of one of the surveys that that our group has been responsible for. So this is the Dawn survey, another narrowband survey, in this case looking for Lyman-alpha emitters at a redshift of 7.7. So this is over a smaller field of view, a much smaller field of view when compared to logger. But interestingly, over this small field of view, we were able to identify 3 Lyman-alpha emitting candidates and spectroscopically follow them up with MOSFIRE, confirming them, suggesting that these objects exist within an ionized bubble region as depicted by this artist rendition. So what we'd like to do is go out to higher redshifts, but in order to really put constraints on the overall conditions of the intergalactic medium, we really need a larger volume, a larger field of view. And so this has resulted in the CIDR project, which is charting ionization during the epoch of reionization. So this is using the same telescope and instrument as logger, but we have a new custom-made narrowband filter. This is shown by this red curve here. So this is at approximately a micron, and you can compare this to the logger narrowband at 964 nanometers. And so this new CIDR narrowband is taking advantage of dark energy cameras, CCDs, which are very red sensitive. Again, we're designing, like the logger narrowband, we're designing it to fall within bright skylines. And we've completed observations of one field. We have preliminary candidates, and we're now trying to obtain our first spectroscopic confirmations for this CIDR project, which will give us, large numbers of Lyman-alpha emitters at a redshift of 7.3 over a volume that's comparable to logger. So one development that has been very exciting for Lyman-alpha science has come with the arrival of James Webb. So James Webb has detected Lyman-alpha out to extremely high redshifts. So it's finding very strong Lyman-alpha emission at a redshift of 7.3, at redshifts of 10.6, and now the current record holder is at a redshift of 13. And so if you look at this figure, you can see that all of the different models are shown here by this orange and blue and magenta curve here. And at a redshift of 13, even the early onset reionization scenarios, which suggest that the neutral hydrogen fraction is in excess of 90%. So even at these very highly neutral regimes in the epoch of reionization, we are able to detect Lyman alpha emission, giving us a lot of hope for the potential for Lyman alpha surveys to be conducted out to extremely high redshifts. However, James Webb is not ideal for probing the the overall condition of the IGM. Its field of view is very small, it has a relatively low, small volume. And let's see if I can change my slide. Yes. Okay, so this is these are simulations that I'm kind of tangentially involved in, but these are simulations that are um, taking a cosmological simulation and then simulating a field of view typical of what you can expect to get with James Webb. And the takeaway here is that you need to cover a bigger area, a larger volume to effectively constrain the ionization percentage. Otherwise, you wind up with these results which have a huge scatter. And so this is where the Roman Space Telescope can play a major role. So here is the field of view of the Roman Space Telescope. So this is showing, this is shown by this, this red outline here. And you can compare this to Hubble and James Webb. So this is a field of view that has about 100 times the field of view of Hubble. And this is going to give us the ability to much more accurately with constrain what's going on with the intergalactic medium. It's much less likely that we'll be biased. And so here it is trying to show this with this figure where James, with the field of view of Hubble, you might just you could study the small field of view and conclude that in this region, the IGM is completely ionized. But if you were to study a field of view comparable to Roman, you would get a much clearer picture. And on the right, this is just showing within the simulation where the Lyman alpha emitting galaxies are located. And if you were to blink them back and forth, you can convince yourself that they are preferentially located in these ionized regions within the simulation as you'd expect. Okay, so these Lyman alpha tests are very are, are 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 going to be able to constrain the timing of reionization, but their power can be increased by combining them with 21 centimeter experiments. And so this is a figure from Ann Hutter's paper in 2019. And this is attempting to show that the cross correlation of Lyman alpha sources is we'll be able to distinguish between different neutral hydrogen fractions if we have a large enough field of view. So this is indicating that we'd need a field of view of around 20 square degrees in order to distinguish between different neutral hydrogen fractions. And so the idea here is that Lyman alpha emitters are preferentially located in ionized regions. 21 centimeters, are trying to directly detect the neutral hydrogen, and so we'd expect them to be anti-correlated with each other, and this can be used to constrain the neutral hydrogen fraction if we have a big enough area. And here, this is showing a proposed field of view for W first, which is now called the Roman Space Telescope. Okay, so I think I've adhered to my time relatively well. So in summary, Lyman alpha galaxies can quantify the timing, pace, and topology of reionization. James Webb is extremely exciting, showing that these objects exist even where the IGM is expected to be almost entirely neutral. And we need to go above and beyond James Webb, though. We need um, a a wider survey to give us an idea of what the overall IGM is, what's going on with the overall IGM. And as I stated with the last slide that I showed, we'd need a, a Lyman-alpha survey that has on the order of tens of square degrees in order to combine it with a 21 centimeter survey. Thanks.
Thank you. Oh, yes, it stopped. So thank you very much, Isak, also for stepping in last minute. I'm sure that was not easy. So I'm sure there are many questions for you. So please, who wants to go first? Yes. Ah, sorry, I didn't see that. Yeah, please go ahead.
Hey, the cross correlation you showed at the end, was it only the spatial cross correlation, or you are also with respect to redshift as well?
So I think one of the main advantages, so this is work that I was not directly involved in, but I think my understanding is one of the main advantages of Lyman-alpha surveys is that, especially for like narrowband, is that they are at a set redshift slice. So it's at a very narrow redshift slice, and then you take those positions of those Lyman-alpha emitters and you're comparing it to the 21 centimeter brightness. But this is not my area of expertise, unfortunately.
Sangeeta is yeah. Today itself, so she will. Other questions? Yes, Harold.
Oh, is it on? Yeah.
Yeah.
Hi, Isaac. I was so you showed the results of the Lager survey, and you compared this to the other constraints on the ionization at redshift, well, different redshift, but I guess we're looking at redshift 7. So it struck me that basically the Lyman-alpha constraints, Lyman-alpha emitter constraints, and the ones about the equivalent width are almost mutually exclusive. Could you comment more on that? Is it? I mean, what are we looking at? So is it a cosmic variance type of problem, or?
Yeah, it's hard for me. It's hard for me to so I think a lot of these LBG in this plot it's both I've combined both the equivalent width evolution and the Lyman-alpha fraction that they're finding. They should in practice give very similar results. I think cosmic variance may be the easiest solution to this. I would say that while there isn't much overlap, there is some, and these are 1 sigma error bars. So, I think it would be interesting to do a survey that tries to control for systematics and does both tests at the same time. So I think with Lager, with us looking at the number density and the equivalent width, we are attempting to do that. I think this would be something that could be interesting to do with Roman Space Telescope also. So with Roman Space Telescope, it has a near-infrared GRISM capability. So with that single instrument, we can look at how Lyman-alpha is evolving from redshifts of about 7.2 onward. And so I think with a single instrument and with the slitless spectroscopic capability of Roman, you could potentially you know, have a large volume where you are able to control for systematics and do many of these Lyman-alpha tests together to give you better constraints. But you know, these are constraints that are you know, taken from the literature, and there are competing groups, and you know, there are some groups that are looking at very similar data sets and still getting results that are, you know, are generally agree within 1 sigma, but are still in tension with each other.
Right. Okay. Yeah, the other option could be it's a model dependence maybe, but yeah, yeah. Let's hope. I guess Roman will definitely be.
Okay. Thanks, thanks, Isak. Let's thank Isak again. And of course, you can put your questions in the Slack as well to both Isak and Sangeeta, I guess.